Good afternoon, good morning, and whatever part of the day it is where you are. We're back with our quantum fluids webinars. I'm hoping you've had a really nice summer, and we have quite a good lineup of talks for this year and also for the next year. So please monitor our site, and also we will be sending updates on the mail list. So today's speaker is Emil Varga. So he, I think, did his PhD at Charles University in Prague, and then he worked as a postdoc in Edmonton, the University of Alberta, in John Davis's group, and now he's back in Prague, and he's got a permanent position. So over to you, Emil.
All right, thank you very much. So, I was said, I'm currently at the Charles University in Prague, in Czech Republic, but all the work I'm going to show today was done in the Davis Lab at the University of Alberta in Canada. And what I'm going to be talking about today is what does helium-4 do when you confine it in a two-dimensional geometry. So, in particular, I want to talk about three things. First, as an introduction, when we talk about superfluid helium, especially superfluid helium-4, we have to distinguish quite carefully about what do we mean by two-dimensional flow and actual two-dimensional confinement. As I say here, 2D or 2D, meaning quasi two-dimensional systems. And what I mean by that is, first we'll talk about quasi two-dimensional flows or quasi two-dimensional turbulence, and then in the second part of my talk, I will move on to strong confinement, where the two-dimensionality of the geometry actually affects the order parameter of the superfluid. Right. So let's start at the beginning. Superfluid helium-4 is a stable phase of liquid helium-4 below about 2.17 Kelvin, and below this phase transition temperature, we can describe it as a mixture of superfluid and normal fluid components, where the superfluid component carries no entropy, no viscosity, and the normal fluid component has both entropy and viscosity. And the ratio of these two components is temperature dependent, where the liquid is almost entirely superfluid below 1 Kelvin. Now, this is basically what happens in the bulk, but since we're talking about confined geometries, we have to kind of very briefly discuss what happens near a wall. So at this 2.17 Kelvin, we have a second order phase transition, and with second order phase transitions, we have some associated order parameter. In the case of helium-4, the order parameter is the macroscopic wave function that is related to the more complicated, but basically Bose-Einstein condensation in the helium, and the superfluid function in some normalization is equal simply to the modulus square of the order parameter. Now, near a wall, this macroscopic wave function has to go to zero smoothly, which sets the form the macroscopic wave function can take, has some sort of relaxation to a bulk value controlled by a correlation line. This, in the low temperature limit, for helium-4 is about 1 angstrom, so atomic size. Now, two-dimensionality, when we talk about flows, is mostly a question of aspect ratio. So classical examples of two-dimensional flows are quite abundant. For example, flows in a soap bubble, or in a more controlled way. We can have a thin layer of salty water, which is driven electromechanically. But if you want to talk about two-dimensional superfluidity itself, we need to get confinement which is comparable to the microscopic small length scale. Which, if you look at this low temperature limit, it might seem hopeless, because, well, modern nanofabrication is pretty good, but we still cannot make atomic size structures with relative ease. But as we'll show later on, this is much simplified near the phase transition. However, this is one of the very few examples where your life is easier when you do superfluid helium-3, where this is much larger, about 10 to 100 nanometers. But so first, let's focus on turbulence in 2D before we move on to the strong confinement. So why is turbulence in 2D interesting? Turbulence in 2 dimensions behaves very differently from turbulence in 3 dimensions. So just as a very brief reminder, what is the basic structure of turbulence in 3D? You have this graph here shows the magnitude of kinetic energy as a function of wave number or inverse scale, inverse spatial scale. Typically, you have some scale where the kinetic energy peaks, where you inject energy, and then in a cascading fashion, like a recursive mechanism which transfers energy from eddies of size to a neighboring size, transfers energy down to smaller and smaller n scales or larger and larger wave numbers until it's dissipated by viscosity. This mechanism is sometimes called the Richardson cascade, where your injection mechanism creates large eddies, which are then broken up into smaller eddies, which are then broken up into smaller and smaller eddies until they are dissipated by viscosity. Now, in 2 dimensions, this very fundamental process that is the cornerstone of our understanding of 3-dimensional turbulence is reversed. Here I show a numerical experiment that I took from this review paper, where energy is injected at some relatively high wave number, and as time progresses forward, rather than these vortices being broken up into even smaller constituents, the energy is built up on larger scales, and energy flows from our very small eddies, which we inject into larger and larger ones, in a process called the inverse energy cascade. This can even lead to something called spectral condensation, where a significant portion of the energy in the system condenses into a very small number of large eddies, typically only 2, which is a kind of a turbulence analog of Bose-Einstein condensation. This was even observed only recently, relatively recently in 2019, in both Bose-Einstein condensates, which is a picture from here, from this paper, and in helium-4 in a very thin layer. Also, just a quick note is that 2-dimensional flows might seem like a fairly academic exercise that's not applicable to anything, but it's actually quite abundant in nature. For example, if you think about our own atmosphere here on Earth, about 80% of the mass of the atmosphere is within 10 kilometers of surface, but the size of the system, or the circumference of Earth, is about 12,000 kilometers. So to a good approximation, it's actually a quasi-2-dimensional system. I don't want to claim that if we understand everything about 2-dimensional turbulence, we'll explain everything about atmosphere. It's a much more complicated system, but in certain cases, a 2-dimensional turbulence system is a relatively good approximation of atmosphere of a planet. Now, how do we look at 2-dimensional turbulence in superfluid helium? In our work that I'll be showing here today, we used nanofluidic Helmholtz resonators. These are devices that look like this, as a picture of them. Inside these devices, here I show a hollowed out volume, a cavity that exists between these 2 glass chips, which is about 1 millimeter in size in XY direction, and about a micrometer or less in vertical direction. Now, this device is thin enough that the normal fluid basically cannot move because of its viscosity, but the superfluid execute a motion like this, which basically is a Helmholtz resonance, as you seen if you ever blowed across an opening of an empty bottle. You hear the whistling or the humming. This is basically the same mechanism. where the oscillating mass is the mass of the helium in the channel, and the restoring force is the pressure that builds up due to compressibility of helium and the formation of the quartz plate here. Now, you see that there is some metal here. That's our way of detecting this motion. Simply as the helium rushes in and out, the pressure builds up or falls and deforms these two metallic electrodes, which results in variation of capacitance, which then we can measure. These Helmholtz modes, since only the superfluid oscillates, can be are related quite directly to the superfluid ratio of the ratio of a superfluid and total densities. So they can be also used as a measurement tool for the superfluid density. Now, as I said, that our signal is essentially a fluctuating capacitance. So all we have to do is build a capacitance bridge, which we use with a help of a center tap transformer, which you balance, and then you watch the fluctuations of current that signify imbalance of the bridge, and to get the mode reproduced in your spectrum that you see in the fluctuations of the current. Right. Now, when these resonances are driven strongly enough, they become nonlinear. The damping in them becomes nonlinear. Here I show in this graph a frequency dependence of the response of two resonators. One was 800 nanometer, this D, and one was about 1 micron, normalized to the drive force. And as we increase the drive, the relative response decreases because the damping grows nonlinearly with force. The turbulence that we observed was published in this paper if you want more details. So on a graph like this, some of the details get lost. So a more detailed information can be obtained by simply tuning the excitation frequency right on the resonance that we are interested in. So driving the Helmholtz mode resonance and slowly continuously changing the amplitude of the driving force. And on these plot I showed the response or the force velocity curves that we've seen. So velocity amplitude as a function of basically the force amplitude for several different temperatures. Sorry, I don't have the actual temperatures here, but this is about 1.4 Kelvin. This is about 1.9 Kelvin, and in between. So immediately you can see that at low velocities or low drives, we see a linear behavior between velocity and pressure gradient. But as we increase, there is some excess damping. So if the system remained linear, the line would just keep going up. But since there is this excess damping, there is some nonlinear mechanism that removes the energy from the flow. Another kind of curious thing is that yes, there is some abrupt transition into turbulent state, but there is more than one turbulent state, more than one stable turbulent state. You can see that there's several parallel lines that show up for a given pressure gradient, or several possible pressure gradient for a given velocity, and some fairly strong hysteretic behavior. So if we look at one of these more closely, at the lowest temperature one here, here I show in the darker curves pressure gradient ramping up, and in the lighter curves, pressure gradient ramping down continuously. So if we look at one of these transition regions in more detail, we see at least three critical velocities. First one, as we increase the velocity, the kind of laminar or modified laminar flow, you can see that there is probably some fourth critical velocity here, falls down into a more dissipative state. And as we decrease the velocity, something very unusual happens on this critical velocity 2, where as we decrease our drive, or as we decrease our drive of the system, our excess dissipation increases further, which is typically not something you expect in a simple turbulent system. And in the critical critical velocity 3, the system becomes laminar again. Here, some of these orange curves which have ramping down velocity were produced by, rather than ramping up and then ramping down, just jumping up to very high velocity and then slowly ramping down. In those cases, typically only the bottom one is stabilized. Typically, we see that the critical velocities have some nice systematic temperature dependence, where above some critical temperature, only 1 and 3 are visible, and this unusual one appears only below about 1.7 Kelvin. Now, why is the excess dissipation there? I already called it turbulence, but I also mentioned that the normal fluid is clamped by viscosity. This is because these devices are so thin that the normal fluid cannot move because of viscosity. And they actually they're actually acoustic resonators for something called forced sound. Now, you're probably familiar with sound types in helium, but the basic is that in the first sound, the two components move in unison and produce ordinary pressure waves as we are used to. Now, second sound is a sound mode which is not associated with fluctuations of density or pressure, but rather temperature and entropy density, and the two components move in opposite phase such that the total density doesn't change. First sound has a similarity with second sound, kind of exists between these two, where normal fluid is clamped by viscosity, but the superfluid can move. Now, the similarity with second sound is that there is a forced difference between the velocities of the two components. Forced velocity between the two components results in motion, or any superfluid velocity results in motion in topological defects that exists in the superfluid components. These are the quantized vortices. Quantized vortices because circulation around them is quantized to typically 1 quantum of circulation. And when these vortices are moving due to the flow of superfluid around them, they scatter off the present excitations that form a normal fluid, thus coupling these two components together and causing dissipation. So typically the dissipation you see when you have any force difference between the superfluid and normal fluid velocities can be, to some first approximation, estimated simply as the number of vortices per unit area times the force difference. And in our case, Vn is 0. Now, we have a good reason now to think that the dissipation is due to quantized vortices. So the task is simplified somewhat only to figuring out what are the quantized vortices doing. So the multi-stability that we see is probably a competition between two different or several different large-scale polarization states. What do we mean by this? As this flow goes past this sharp corner here, the induced vorticity has some very strong polarization, a very strong distribution of positively and negatively oriented vorticity. So it's probably injecting vortices in a manner that agrees with this large-scale simulation. We capture this by a simple quasi two-dimensional vortex dynamics model that looks like this, where we model independently in a coupled way the time evolution of the number of positive and negative vortices, assuming that there is a positive definite sign can be assigned to vortices in the flow channel, where we have a simple some sort of splitting and advection out of the domain, which we'll call some loss of vorticity, and splitting from the other species. By the way, splitting would not happen in 2 dimensions, so that's what we call quasi 2 dimensions. Then we have a 2-dimensional mechanism, which is simply annihilation by collision of vortices opposite sign, and creation of new vortices by this large scale shear. Now, our experiment is not sensitive to polarization of the vortice; it's only sensitive to the absolute number. So we have to change our variable slightly, the total number and some polarization parameter, where we get two new equations based on the substitution. Now, what exactly this polarization parameter is has to be interpreted with a little bit of care. I won't go into the details, but in the end, it turns out what appears to be the most sensible way of interpreting it is basically a Fourier parameter, or like a Fourier mode of how the vortices are distributed in the channel, meaning that if the flow comes like this, and the sharp corners are here, then with s equals s larger than 0, the vortices will be like this, and s less than 0 would be like this. Now, this set of two dynamical equations, which are nonlinear and coupled, turns out to have two distinct solutions in vortex number. On this graph, I show on y-axis the vortex polarization parameter, and on the x-axis the total vortex number in the model. And all these little points show initial conditions, and these lines are trajectories that evolve towards two possible stable states. Now, if we take all of these trajectories and plot them as a function of time, we see that the total number of vortices, again, depending on the initial conditions, falls into two stable states. So that already captures the more than one stable state of steady turbulence that we see. But an interesting thing happens is that as we start to ramp G and the generation term and the polarization generation term linearly down in time, which kind of models the velocity ramp down experiment, we see a temporary increase in the total number of vortices, and thus the temporary increase in the observed excess dissipation in a manner which is very similar to our experimental observation, which happens because one of the polarization states collapses and now becomes temporarily aligned with the GS with the sign of the GS, and thus temporarily increasing the total vortex number. So even though this model is kind of crude and has still kind of unresolved couplings to the actual physical parameters, we already captured some basic ideas here, that we see multi-stable behavior, and we see this unusual backward transition. But going further and deeper into this issue is a task for the future. And now I will move on to the second part of my talk, which is actual finite-size effects, which is influence of the geometry on the order parameter and two-dimensional superfluidity. So I repeat this slide here to remind you that we would have to, in order to see any significant effect of our confinement on the superfluidity itself, we would have to get to sizes comparable with the correlation length, which is only about 1 angstrom. This is basically practically impossible. However, life becomes a bit easier if we approach the phase transition, the superfluid phase transition, where, as I show on this graph, the correlation length as a function of reduced temperature, so T over T equals 1 is the phase transition. We see that the correlation length diverges. In practice, it will be clipped by the size of the system, and it diverges with some critical exponent too. Now, this basically means that almost whatever the size of the system is, the question of observing finite-size effects becomes whether you can stabilize temperature close enough to the transition. For example, in this paper by Lipa and co-workers in 2000, they observed finite-size effects and specific heat of superfluid helium on 57 micron confinement, which is actually quite large. But all they had to do is to stabilize temperature within tens of nanokelvin of the phase transition. Yeah. So it's a trade-off how good your temperature stability is and how small your confinement is. Okay, so now if the correlation length is the only relevant small scale, the a lot of physical quantities will be modified, but their modification should follow some scaling relations. So we can broadly distinguish two classes where the correlation length is much smaller than the system size. Then we expect in two-dimensional confinement only some perturbation to our observed quantities like or thermodynamic quantities like free energy. Only some perturbation due to a surface term. On the other hand, when our system size becomes comparable to the correlation length, some more general behavior is expected, but again, the behavior should be universal for a given type of geometry, and it should be a universal function of a dimensionless parameter that looks like this, which is basically the size of the system rescaled by the temperature dependent correlation length. This type of behavior has been observed to a pretty good, very good accuracy, for example, in heat capacity above the lambda transition, but close to it, of course, where on this graph I show data from this review paper, where we see the change in heat capacity compared to a bulk value as a function of this dimensional scaling variable. And you can see a beautiful collapse of all data across more than three orders of magnitude in confinement. On the other hand, we do the same approach for superfluid density near the phase transition, below it, of course, this time. We see no such behavior. And regardless of the scaling of the axis that we choose, the data that we see from multiple the data that people saw in the past from multiple confinements do not follow any universal scaling laws. Now, why is this? This has been a puzzle for quite a while, and we decided to have a look at this using our Helmholtz devices. But as we said, that to observe these finite size effects with a micron scale confinement, we would have to have much higher temperature stability than our fridges were capable of. So instead, we created a confinement which is much smaller, 50 nanometers or less, and this resulted in this paper. If you want to find out more. So the devices that we use here are basically two ordinary Helmholtz resonators placed side by side on single chip, bridged together with a very strongly confined channel. All of the geometry on the chip is defined through wet etching, so with hydrofluoric acid, which is a fairly well controlled procedure where creating channels which has only about 70 nanometer step or 25 nanometer step is relatively easy. The total confinement is twice this step because there are two chips which come together and are placed on top of each other. So the total channel size is double. And a resonator like this will support multiple Helmholtz modes. It's questionable whether this can still be called a Helmholtz mode or whether we should call it a fourth sound acoustic mode. But the basic of it is that these two modes look like this. Here I show in these cartoons the pressure amplitude in the mode. So in the fundamental mode, the pressure in the two basins, these two circular regions here, oscillates again in unison. And in the higher order mode, they oscillate in anti-phase. Now the important thing here is that in this fundamental mode, there is no pressure gradient across this strongly confined channel, but in this higher mode, there is a strong pressure gradient and thus flow across the strongly confined channel. So we have kind of in situ on a single chip comparison of strongly and relatively weakly confined helium. And the velocity in this mode looks something like this. So the velocity is actually concentrated in this central channel. Now, since our temperature stability near the phase transition was about 1 millikelvin, we do not expect to see any measurable deviation from bulk behavior in a 1 micron or 700 nanometer confinement. So this is basically bulk behavior, and we can estimate the bulk superfluid fraction simply as a ratio of the frequency of the mode that we observe normalized to its zero temperature value. As I showed very early in the talk, there is a correspondence between the frequency of the fourth sound acoustic mode and the frequency. Similarly, we can estimate the confined superfluid fraction from splitting of these two modes. Right, so now we have a way of measuring confined and bulk-like superfluid fractions. So we can have a look at them. And as you see on this plot of superfluid density versus temperature, there is a very slight depression compared to the bulk value in black, and both at 25 and 50 nanometer data are slightly below that. To have a slightly better look, we can have a look at the normal fluid density enhancement, which is just the increase in the normal fluid density or negative superfluid density in confinement compared to the bulk. Now, I'm going to plot this in just a slightly more different way, where the slightly rescaled by root temperature excess normal fluid in logarithmic axis is plotted as a function of inverse temperature. This shows a beautiful exponential behavior, which can be entirely accounted for by an expression of this type, where this expression gives a contribution to the normal fluid density from the roton part of the quasi-particle excitation spectrum in helium. With one important difference is that in bulk we observe the observed roton gap by neutron scattering in this paper was about 9 Kelvin, and that's the typical value, about 9 Kelvin. Our data show about 5 Kelvin. 5 Kelvin roton gap. Another important thing here is that, as I mentioned in the introduction of this part, is that as we go from low temperature limit to high temperature limit, we should expect some change from like surface dominated behavior to a regime where the correlation length is comparable to the system size, but we see no change in qualitative behavior. So it seems like all of this is just due to these rotons that are somehow associated with the surface. Now, the surface bound excitations are new. People have seen it and predicted it for almost 50 years now, and they were seen both theoretically and in thermodynamic data in porous Viper. Again, with gap parameters from ranging from 5 Kelvin to about 6 Kelvin. Another thing that we can do with these resonators, since they are submerged in superfluid helium, we can pressurize them. We can increase pressure on them, which is often a problem with these micron scale confinements, which are contacted directly because they would explode. But in our case, since they're submerged, we can increase the pressure all the way to solidification pressure, and we see that these curves are just shifted but remain parallel to each other. So there is no change in the gap parameter. This is in quite strong contrast with what's observed in bulk. Again, I show data from this Swiss paper here by Andre Gottfried and co-workers, where they very accurately measured the gap dependence on pressure, and the change can be almost 20%. So with the surface rotons, we don't see anything such that. So now that we kind of convinced ourselves that there's a new excitation that lies on the surface, we can just apply this theory and find out how the excess normal fluid should scale with confinement, and find that this product of the excess normal fluid density times the confinement should remain a confinement independent function, a universal function of only temperature. And we see that that's not quite the case. There is still some confinement dependence that's not captured by this model. And what this is can get a clue from numerical simulations that, for example, were done by a group of Professor Reato a couple of years ago, where they saw again a similar behavior in their Monte Carlo simulations, where the Roton gap is a very slow or weak function of the density of the layer that they simulated, but the Roton wave vector was linearly increasing. Now, so using this this idea that the Roton wave vector is changing as we are changing the pressure, we can write a scaling theory that captures both the pressure dependence and the additional confinement dependence, and results in a very nice collapse of all the data that we see. This confinement dependence comes from the idea that the pressure varies not only because of the applied pressure from the bulk, but also due to the van der Waals attraction of helium to the substrate. And as we change the confinement, we are changing the influence that one wall has on the other. This is relatively weak, but comes at the cost of introducing it comes, of course, at the cost of introducing another fitting parameter. It's a need because it captures both pressure and confinement dependence within one framework. Right. So this was kind of the finite size effect on the superfluid density, but I also kind of promised a two-dimensional superfluidity itself. Now, in order to get to the superfluid two-dimensional superfluidity, we need confinement which is comparable to the actual microscopic length scale. As we approach in this two-dimensional system, as we approach the bulk transition temperature, the superfluidity is actually lost below the bulk transition temperature through something called the Kosteles-Taulos mechanism. In these very thin layers of helium at low temperatures, you can imagine that bound or vortex pairs, vortex anti-vortex pairs are excitations with finite energy, so there will be some population of them in the film only due to thermal fluctuations. Now, as the temperature is increased and approaches the critical temperature of the Kosteles-Taulos phase transition, this kind of gas of molecules becomes a plasma, and at this point, this is a fairly sharp transition. The system stops being able to support superflow, a dissipation-less flow, which leads to a so-called topological or Kosteles-Taulos phase transition. At this phase transition, the superfluidity is lost discontinuously, and is given the loss of superfluid density is given only by the confinement and a universal constant, which is given by the mass of the helium atom, Boltzmann constant and Planck's constant is about this value. This I cannot do this topic justice. This is just a tip of a very deep iceberg that won these three guys the Nobel Prize 6 years ago. Now, as we approach this transition with our devices, we do indeed see something that's consistent with discontinuous loss of the superfluid density on the level that's roughly predicted by the theory. You can see this huge increase in the error bars here. It's logarithmic axis, but it still increases quite significantly, which is due to temperature control. Because the temperature dependence of the superfluid density here is very rapid, and if your temperature control is only about 1 millikelvin, you get large error bar. And yeah, we see something that's consistent with the Kosteles-Taulos phase transition. Now, the way people typically in the past tested Kosteles-Taulos theory is they varied the thickness of the film, and thus they changed the critical temperature and the superfluid density of the critical temperature was then related through a linear relationship. Now, in a fixed chip which has a fully confined geometry, we cannot in situ tune the confinement, but we can change the total density and bulk transition temperature through changing the bulk pressure. On this plot, I show the superfluid density as a function of temperature for a range of pressures. Here, the black points are the bulk-like data, and the points with the color scale correspond to the confined data in the 25 nanometer confinement. And you can see both the DC is decreasing. So as the DC is decreasing, the rawest jump at the transition should be decreasing with it, since D remains constant and the universal constant remains constant. But if we plot everything together, surprisingly, we don't see anything. We don't see any change in the behavior just above the transition. This plot shows the superfluid density as a function of reduced temperature, where here this T lambda is the pressure dependent bulk transition temperature, and we see a perfect collapse, even though the change due to the pressure that we induced in the Kosterlitz jump should change about this much, as this range of lines here show, which is kind of on the edge of our resolution, but it's still invisible in our data. And the reason for this is currently not understood. And I should also point out that there were past experiments where they tried pressurizing helium-4 films in some other clever ways. For example, this paper by Murakawa and coworkers, where they pressurized a helium-4 film with a normal helium-3 bath above it, and they actually saw fairly strong temperature dependence of the film transition temperature. So also the discrepancy with this past works is not fully understood. So that brings me to conclusions a few minutes before I'm supposed to end. So the quasi-two-dimensional quantum turbulence is a quite interesting system. It supports more than one large-scale and stable state. We see suppression of superfluidity in strongly confined system, which is dominated by surface effects, without any involvement, it seems, of the correlation length or the ratio of correlation length to system size. And finally, the Kosterlitz transition possibly shows some unexplained lack of pressure dependence. So with that, thank you very much for your attention. And before I give up my back to the organizers, we have a postdoc and funded PhD positions open, and they're also listed on this website of the webinars, and you can just contact me if you're interested. Okay, thank you very much. Thank you very much for your attention.
Yeah, thanks a lot, Emil, for the exciting talk. Yeah, any questions? Please raise your hand on Zoom.
Do I see the? I don't see the hands. Is someone else moderating, or oh, maybe?
Well, I'm guessing if you have a question, just unmute yourself and
yeah.
Can I ask a question?
Yes.
Okay. Well, I'll put my video on. Thank you for this beautiful talk, and I really enjoyed it, and a very beautiful experiment. But one thing that puzzled me is when you compare to our neutron scattering data, you compare as a function of pressure. You mentioned the pressure dependence, and in your analysis, I don't see any pressure dependence of the effective mass taken into account. You see in the formula, so I agree the gap, okay, it's the exponential, so that's okay. You see a small gap, which is consistent with neutron scattering data of 2D rotons in different substrates. And but then there is a pressure dependence of the roton energy and also of the effective mass, the curvature of the dispersion relation. So you choose to put some constant mass. I saw that you put m star in the formula, but you don't say what is in this m star.
Yes, that's a very good point. I kind of glossed over this. We set m star to be a constant, in pressure independent constant, based on some Monte Carlo simulations that I don't have this don't cite here. It's about 1.4, if I remember correctly, of mass of helium atom. And the reason we don't put too much emphasis on this effective mass is because its influence on the excess normal density is much weaker than of the wave vector, which comes in
square root
power 3, and we know that the wave vector is changing quite strongly. Yes. You're absolutely right. You're absolutely right. This is a simplifying assumption that we made.
But I agree that it's okay. It's not so that in the square root it will not make a big difference. But somehow, yes, it does. Yes.
Yeah, absolutely. This is a simplifying assumption that we had to make in order, because we fit one parameter and we cannot extract two parameters which are multiplied from one fit parameter. So we kind of brushed the effective mass under a rug in a way, assuming that it will be less important than the wave vector.
For the 2D roton, did you have a look at the calculations by Eckhard Krawczyk, Brad Clements? There is a paper, the first author is Brad Clements, where they compared to the neutron data that we had taken on helium films of different thicknesses. And so they see the evolution of the roton, the 2D roton.
Yes, I believe I've read that paper. There's several of them, and I forget things easily. But
yeah, it's complicated. It's complex literature.
Yeah. And from what I remember, the effective mass here, because of this is square root and because of this is 3, produces a relatively weak effect. What we did check, and I don't show it here, is that if we assume the effective mass to be something from these curves, not just from the slopes but from the curves themselves, we can estimate the wave vector and the wavelength of the roton, and it fits with both neutron data in confinement and simulations pretty well.
Okay. Well, thank you. Congratulations. Nice job.
Thank you very much. That was a very, very good point.
Well, thanks, Henry. So I think Igor has a question.
Yes. Somehow my hand was always disappeared. So thank you very much for the nice talk. I have a few questions. You have shown that the omega of the resonance is proportional to square of rho s over total rho square. Can you explain it, please? No. Earlier.
Earlier
slide.
This one.
Yeah, exactly.
Yeah. So, well, I won't be able to reproduce the derivation from my head, unfortunately. But as you change the rho s, you change the effective mass, and you also change how much mass flows into the basin, how much so that changes by how much you pressurize the basin in the cycle, which changes the effective constant as well. And if you just write down the equation of continuity and compressibility for helium, you work it out and you get this expression. This expression is very common for any devices that use fourth sound in helium.
So you mean that effective spring constant is proportional to ρs only?
It's proportional to ρs in some power. Power.
And the mass is proportional to ρ square.
Effective mass is proportional to ρs, and effective spring constant is proportional to well, looking at this must be proportional to ρs 1.5.
Okay.
I don't have the derivation here. It's in.
Yes, no problem. Just a question. Yes.
Yeah, but both K effective and M effective is a function of ρs. That's why it ends up looking like this.
Okay. Thank you. Can I ask one more question?
Absolutely.
Yeah. So you're supposed to have a lot of vortices in your system, and how much they affect the spring constant, because they have finite and not very small line tension. So under deformation, they should like resist.
That's a very good point. However, I don't know how many vortices are there inside this circular basin here. Because if you look at this K effective is due to what happens here, but the vortices will exist here.
Oh,
that's
okay.
where the flow is. So it's a very interesting question, but I suspect that the amount of vortices inside the basin is there mostly due to pinning because of the cooling of the device, because of transition through the superfluid transition, and is not affected much by the turbulence. But I'm not sure, and I think it's a very interesting question.
Yeah, thank you. Can I ask one more question?
If the organizers are okay with it, then I'm too.
Yes. You have quite thick slab of helium compared to the correlation length. You said about this, yeah, and but still you see some sufficient effect of the thickness, right?
Of what? Sorry, didn't understand that last word.
You have quite large thickness of the slab compared to the correlation length, but still you see the effect of the thickness. On the
not in this case. With these hundreds of nanometers, or even several microns or 1 micron thick devices, we don't see any deviation from bulk.
Okay, then still one question. What is the length of the free path at let's say 1 Kelvin when you see kind of transition on the oscillation frequency? I just can't remember, but you probably know.
Length of
free path lengths of the
excitations?
Yeah. Maybe this matters more than the correlation lengths.
At 1 Kelvin, it should still be a continuum, and that's how in all of these studies we treated normal fluid as a continuum. So I don't know. I must admit I don't know the mean free path off the top of my head.
Okay, thank you very much.
Thanks. Any more questions? Yeah, I'll then ask a sort of question. So with your thinnest channel, So you've tried to maybe observe the like Kibble-Zurek mechanism of producing vortices, so you can cool down through the transition at various speeds, and then maybe at low temperatures some sort of dissipation would depend on the number of vortices pinned in your channel. Is it a possible experiment?
That is a possible experiment, and we tried, unfortunately not with the thinnest channels. We tried with channels about 500 nanometers in size, in a geometry that looks like this, and we haven't seen anything reproducible and systematic. But we haven't tried with the thinnest ones. We should have.
Okay, well, that's something for the future. All right, so if there are no more questions, and we're coming to 5 o'clock, then thanks everyone for attending, and we'll have another seminar in 2 weeks' time and another talk from Prague. It's going to be David Schmorenza. So the ad is already on the website, and I will send the emails in a week's time or so to remind you. Thanks a lot. Bye.
Thank you.